So now let us make the cost function. We did the feed forward function, time for the cost function. So I should just say cost function like that all the time. We need energy. Cost function, that's fine. So we're gonna do the cost function. It's pretty similar to what we usually do. Just take some math, translate it into code. Here is the equation. If you remember it from whatever the gradient descent lesson, either lesson 7 or 8. So hopefully you remember this. If not, the video is either 7 or 8, so you can find it. What we're gonna do is we're gonna break this down. So the first part is we gotta take, this difference over here, we gotta square it, and then we gotta sum over, all of the examples. And finally we divide over, the sum, because it's like we're taking an average, we're taking an average cost. We're finding out on average how far apart is the prediction from the actual output that we want. And we're doing it, over m examples. This is the mean squared error function. One thing to keep in mind is this is not the best function, the best cost function for what we're doing, but for now it'll do, and later on we'll figure out what are some other cost functions we can use. So for now, let's just translate the code into math. As always, define a cost function. That's the function, cost function. We're gonna have some input. So here, what we're gonna need to do is we're gonna first need to generate y hat. Okay, we're gonna need to generate the prediction. For that, we need the x and theta values, like we saw here. And another thing that we need is we need the y value. We didn't need the y value before, now we do. So that's how I think, what does the function need? It needs all the things from the function, other functions it relies on. That's the parameters it needs. And any new parameters in this equation. So the first thing we got to do is we got to generate the prediction y hat. And luckily, we can do that not just for like example I, we can do that for all of the examples at once. Because we got an amazing function right here that we call it Vectorize. It can work with vectors, matrices, not just one scalar. It can work with a group of numbers all at once. This is actually faster. We'll talk a little bit about that later, about speed of different algorithms, but for now, just know that's efficient. I'm going to use the y value to actually generate, this m parameter, the number of examples. Remember the y shape? We saw it earlier. It was just 4,238 long, one-dimensional. That's why I take to get the value of m, I just take y dot shape, and then I take the 0th element of the tuple that is returned. You see the tuple right here. I just take the first element of that tuple, and that gives me the value that I need, m. So we got two of these values in the formula now, m and y hat, and we were passed in the original value y, the labels. So now, once we've gotten the right variables we need, that's a tip for like how do you think about coding functions. First, you got to get all the variables you need. After we have all the variables we need, then we can start computing. So first part, we need to get the difference squared. So we just take the prediction minus the label, just like we see here, y hat minus y. One thing to keep in mind, we could write a for loop and go over all the examples, from I equals 0 to m, just like we see here. However, there's no reason to do that because with Numpy, what's actually going on here is it's performing a vector-vector subtraction. And over here, it is squaring every single element in the vector. That's something to note for Numpy. If you ever, write a minus sign, a plus sign, a division sign, a multiplication sign, a squared sign, it's doing that to each element in the vector. So it's automatically doing element-wise operations. I hope you remember what that word means from the matrix operations lesson. Is that cool? All right. So that's the first part done. Yay! So we got like all of this bit in red. Now let's do that summation and dividing by the average bit. So luckily, Numpy has another method for us, sum. And what the sum method does is it just, it sums everything. So, I did that squashing motion because it's like you have a vector, it's long. It has, m examples. Both prediction and y are m long. And what NumPy does is it adds up every single number in that vector. So it's like it squashes it into one number. And then I just divide by m, just like we divide by m here. So it's like we're adding up every single example. Then we divide by the number of examples, we get the average. So we're getting the average cost per example. And that's what the function returns. Is that cool? I'm going to quickly check the questions here. Can't we do m is equal to y instead of m is equal to shape 0? No, we can't, because m is the number of examples. So let me print out here to clarify things. Let's print out y, and let's print out m. So y is going to be a very long vector that is going to be like zeros and ones. Does the patient have coronary heart disease or not? The shape of y, it's going to be this tuple that we saw up here. So it's going to be, this tuple, because it's like a one-dimensional vector, so it has one number in the tuple, one element in the tuple, and that number is the number of examples. It's m. That's why we get m as the first element of that tuple. Hopefully that helps. Yeah. Let's see the chats. Cool. Any other questions? Feel free to ask. All right. As always, what do? We got to test the function. So luckily for us, we already defined all of these values earlier. So we have, x already defined, the variable earlier. We generated a data value. We already had y defined. We got x and y up here. So we can just, pass in these values. Cost is equal to the cost function, x, y data. Remember, you have to pass in the arguments here in the order that the parameters are read here. Remember, arguments just means parameters. Python people are stupid, so they just called it different things. So we put in the cost function, and lo and behold, we get out a cost. So, 0.15, we're getting out a real number. That's what we want. Yay, cost function working. That's like the third quarter done. We're almost done. We just have one last quarter to go. We just got to write the gradient descent and gradient computation function. Here, take a deep breath, okay? This one's going to be it's going to be hard. It's going to be messy. It's going to be confusing. You're not going to like me. But unfortunately, we're going to have to write these functions. So brace yourselves. Are you braced? Are you ready? Deep breaths taken. All right? So expect the hardship. It is going to come. We, as ever, are going to need to translate some equations, math. That's our job today. We're translating math into code. That's what we do with NumPy. We're going to need to translate these equations into code. Now I wanna explain these equations again, because over here I made a correction. So this is different than what you saw in lesson number 8. First equation, so theta is going to be equal to theta minus, this hyperparameter, that's the learning rate, times the gradient. Remember, the gradient just means what's the partial of the cost by the partial of each parameter theta j. So j ranges from 0 to n. So that's like, okay, we have a parameter for, the male we have a parameter that gets multiplied by this input feature male. We have a parameter that gets multiplied by age, and so on and so on. So this is theta 0, 1, 2, 3, and 4. Well, it's not theta 1, it's not theta, but each of these input features, x0, 1, 2, 3, and 4, gets a parameter for it that it will be multiplied by, theta 0, 1, 2, 3, 4. So that's why over here, this partial of c by partial of theta j, J is going to range from like 0, 1, 2, 3, and 4. So it's going to have like 5 total values. Remember, in Python, we start counting at 0, so everything just becomes 0, up to, but not including n. So J will go from 0 to 0 up to, but not including 5. That's the number of input features. Now, when we're doing that, we're calculating this, this term for one data parameter. This gradient is just a storage container for all of these. So what's partial C by partial theta 1? What's partial C by partial theta 2? And so on and so on. This is also, a vector. So it's kind of like we're taking the vectors and we're adjusting their values. We're subtracting away this bit, and it's going to adjust, the value for each parameter. Is this part making sense? Now, here, I don't know if you can see too well. Let's see if we can maybe try and zoom in. Well, the general idea is we have some equations for each of these parts of the partial derivative. So for each partial derivative that we're computing, and that's not helping, I just made it smaller. Anyways, so for each partial derivative that we're computing, where we're taking a partial derivative for one single parameter at a time, we use this expression. So partial C by partial theta j. Oh, this should also have a j. One more correction to be made. Don't worry, by the time you go back to designate, that correction will have been made. So remember, it's a little bit, we're using the chain rule here. That's the backpropagation algorithm, never stop taking the chain rule. And we're doing that with the goal of getting this gradient vector. So this is the part we're going to have to compute. Remember, this is working because it's kind of like these cancel out. So, I cancel out this bottom denominator with this top numerator, then this one with this one, that one with that one, until we're left with partial C by partial theta. Cool? Now, for each of these expressions, remember, you can take a derivative. And I didn't prove to you, how I got those derivative values. However, I gave you the equations that you needed. So these three equations plus this equation, that's what I'm getting all of these values for. So this time, these are actually the right values, I promise. I double checked, except I didn't put this J here. I'll put in the J. But what this is doing is, if you take my word for these values, or if you go back to the equations and try to do the derivations yourself, then we're going to have to use each of these terms, multiply them together to be able to find this expression. And one thing to note here, so for each partial derivative, okay, for each partial C by partial theta j, for each parameter that we're finding a partial derivative for, we are basically taking the average across all the examples. Now, I want to really explain to you what this means. So let's take a second to really understand that. Remember, for each column here, okay, for each input feature, we're going to have one data. We're going to have one parameter. What we're doing is we're summing across all of the examples. So, what are all of the examples? What are their values for male? And we're going to average the adjustment to that data parameter that goes with this input feature across all the examples. So we're not just like, we have a patient Shannon, and to better predict Shannon's output, to better have a data parameter that we can multiply by this input feature, we'll just, take a look at how much Shannon's prediction would improve if we made a tiny change in that data parameter. We're saying consider all 4,238 patients and make the average adjustment to that parameter. And we're going to do it with the first input feature and its corresponding parameter. We're going to do it with the second input feature and its corresponding parameter, and we're going to do that individually for each of these input features and their corresponding parameters. Is that making sense? I know I said a bunch of big words, so pause to let that sink in. Anyone want to try and say it back to me? Just to make sure that maybe someone is hopefully understanding me. Here's the formula again, if that helps you. Try and repeat back what I said. Anyone up for the challenge? All right, so, okay, Aditya, go for it.
Each of the features has one weight with it.
Mm-hmm.
So to calculate that weight, you have to take the average of all of the examples to get the difference between the derivative. Well, I understand why you need to take the average.
Okay, yeah, that's a good start. So you're right in the part that we're taking an average across all the examples. Now, what are we taking an average for? What we're taking an average for is all of this business. All of this business is just a number at the end of the day. So, you know, y hat at I, so that's like some example, minus y, so that might be like, say we predicted 1, this is the actual label turned out to be 0. So we might go 2 times 1. So that is a scalar number. 1 is a scalar number. The output here is going to be a scalar number. This input feature value is a scalar number. So once we're multiplying all of these scalar numbers together, we get out a scalar number. Yeah? So what we're doing is we're computing a scalar number. What the scalar number represents is, for that example, for that one example, how much would we need to change the parameter theta j? So, theta 1, maybe that corresponds to the male input feature. How much will we need to change that to make the cost go down? Okay, remember that's what the gradient does. Once we've computed that for one example, and then the next example, and then the next example, we're going to add together all the examples, divide by m. What that does is we're taking the average change that we need across all of the examples. So all of this is just a number, and that number represents the change we want to make for this one parameter so that we can reduce the cost. Then we're going to average across all the examples so that we're not just focused on, okay, for this one example, how much do we want to change this parameter? We want to do it for all the examples. Yeah?
Yeah, I get it now. It's much more clear.
Okay, hopefully that makes sense. And remember what the relationship between this and the gradient is. The gradient is just a storage container for all of these. So from 0 to n, all of these j's. So what our gradient descent algorithm is going to need to do, first part is, as I broke down in the checklist, we're just going to compute the gradient function. Just get we're just going to get this value over here. And then once we've gotten, we've computed this value for theta 0, then theta 1, then theta 2, theta 3, theta 4. Then we're going to package all of those into a vector that we're going to send to another function, and it will run the subtraction. Okay? So first part, again, we're just translating math to code here. This is going to be a bit ugly. So what we're going to need to do is, remember, we need to make a function that can get these values from 0 to n. So we're going to need to get a function that can compute this term for all the all the parameters. So the way we can do this is we could, make a for loop. It goes from 0 to n, and each time in the for loop, we're trying to compute this. We're trying to compute this value, which is in the end just a scalar number. Now, when we're doing that for loop, each term that we're computing here, that itself is going to need a for loop because we're going to need to go through each example. So we're going to need to go through each example for each parameter. So we have one for loop, it goes from 0 to n. Then we have another for loop. It goes from 0 to m. Is that making sense? Aris? Kinda. So let's try and look a little bit at the code and keep in mind what I just said. We're getting one for loop to go through 0 to n so that we can compute, dc by d theta 0, dc by d theta 1, and so on and so on. Another for loop to go through all of these examples, because for each of these, we're going to need to go through all of the examples to compute this expression. So this is going to be called gradient ICI, because it's a ICI implementation of how do we compute gradients. The values I'm going to take in here are the prediction, y hat. We're going to take in x, because if you remember the way that we compute the weighted input, that is x and theta. Yeah. So we're going to take in all of these values so that, we can later compute things. Remember the first part, let's just get all the variables we need. So we have the prediction, that's y hat. We have x, which is, it's a big vector containing all of these x's, each of the individual input features. We have the y, which is, right here. One thing that we need is we need a variable m for this formula, and we need a variable n because j goes from 0 to n. So m, remember, that's the number of examples. The way that I got that was y.shape at 0 again, because y.shape, it's just a tuple. It represents the number of examples because for each example we have one label. And n I got from, again, x is a m by n vector. So it's number of examples by number of input features, as you saw here. I shouldn't say vector, I should say matrix. So m by n. So I got x dot shape. It's going to be 4238 by 5. I got the last number here to get n. Cool. Is that making sense on the values, how we got them? Aditya?
So why did you do -1?
-1 means take the last element. So up here you can see the shape of this is 4,238 by 5. I can see that 5 is the last element. That's the one I want, the number of features.
Right.
That's n. So we got the values we need. We have all 5 of these things, all 5 of the variables. Now we're going to get into the for loops. So here's what I'm going to do. Here's the first thing I'm going to do, okay? The first thing I'm going to do is I'm going to compute this term right here. I'm going to do it as a vector because later on, I can loop through all the values. But the way that I do that is just 2 times y hat minus y. Y hat is just the prediction. So this is it's just using a Numpy subtraction, so subtraction here. And it's cost by pred. So the partial of cost by the partial of the predictions. This returns a m by 1 vector. So m as in the number of examples. So I've done this for each example, which I can loop through later. Making sense so far? Next line is I'm going to do the same thing for the second term over here. So I'm going to get the partial of, this is the output of the sigmoid, that's the activation, by partial of the input of the sigmoid, that's the weighted input. Remember, sigmoid function, output is activation, input is the weighted input Z. So I got sigmoid out by sigmoid in by just taking the sigmoid derivative function that we defined earlier. Remember we did that up here, sigmoid prime, we defined it. So it's just calculating that again. It's done it for all of the examples. We're gonna loop through it later. Cool. So I've computed these terms for all of the examples. This one I don't need to compute for all of the examples because, it's in the X matrix itself. Keep in mind the dimensions. This is really important when we're making these types of algorithms. We need to keep in mind the dimensions. So 1 is a m by 1 vector. We have this. It's based on, the prediction by and the y. Those are both, they have m examples. The other is m by n because it's based on the dimension of the x vector, x matrix. Remember, m examples by n input features. Now we're going to actually make a few for loops. I know this is scary. I warned you about it. So here's what we're going to do. The first thing we're going to do is we're going to make a for loop that goes through 0 to n. It goes through all the values of j. Yeah? Now, when we're going through all of these values, 0 through j, what we need to do is we need to compute this term. And to compute this term, we got to go through all the values 1 through m, from 0 to m. And remember, we're doing a summation. So I'm going to compute each of these values. Every single time I go through an example, I'm going to compute this. Okay? So every single time I go through an example, I'm going to compute all of these things right here. And then I'm going to keep adding it to a total. So I'm basically like defining a summation operation right here. Sure, Sarah, that makes sense. So here, I made a summation result. It's going to be, set to 0 at first, and then every single time I go through this inner for loop, I'm going through all of the examples from the 0th example to the mth example. And every single time, I'm just computing this inner expression. So the value, this value here in the brackets, it is the value for the current example. And here you see this first term, cost by prediction. I just, computed that earlier. So I'm just getting the ith value for that. So, the value for the ith example. Over here, sigmoid out by sigmoid in. That again, I computed here. That corresponds to this term. I'm multiplying these two together, just like I am, up here. I don't need to multiply by 1 because, the 1, when you multiply, it doesn't do anything. Keep in mind, I have these two indices, I and j, for both this x value and the sigmoid derivative. Why am I doing that? It's because the I index, it goes through all of the, it goes through all of the examples from I equals 0 to m, and the jth index is going through all of the input features from n equals 0 to n equals 5. Yeah? So this is like the most important part to understand. This code just corresponds to this thing up here in brackets. And I need to go through and loop through. I need these for loops so that I can compute this. What I do when I compute this is I add it to the summation. Is this making sense? I'm going through all of the input features from 0 to n. I'm going through all of the examples from 0 to m, And every single time I compute this expression, which is just what we see here in the brackets. And then I'm doing the summation operation. So I start off by initializing the summation to 0, because like we haven't added anything to it yet. And every single time I calculate this value in brackets, I add it to the result. So I'm adding all of these values from 0 to m. Hopefully this is making sense. Aditya, yeah? Remember, there's one last part to this. So one thing that I have to do still is I have to divide by m. Again, just translating the math to the code. So I get the average. I divide by m. I got the summation by adding up. This code was the code that added. And then in the end, I just divided by m. Now this formula is done. So this formula, remember, computes one value, partial c by partial theta j. Thank you for being happy, Aditya. What I have to do for the gradients is I have to do this for all of the values of j, not for like just theta 0, but theta 1, 2, 3, and 4. So the way I do that is I've initialized this gradient. So there's this function np.zeros, there's this method np.zeros. Again, I just pass in the shape that I want. So, I have n parameters. That's why I created this gradient with like n placeholders. And each time I go through like theta j, remember I'm going through this in the for loop. Then I say, okay, gradient at 0, gradient at 1, gradient at 2, gradient 3, gradient 4 is this result that we just computed. Making sense? All right, this is a really bad way to do things, but this is like basically that's the basic beginner way. We're just translating the code literally to the math. As always, we can test things out, but you see, our pred is not defined. Let me make sure that we have a prediction over here. Pred, my session reset. So let me just run these things again. Sometimes you might have to do that. Make sure I have these values and y and these functions and these and this. Okay, there we go. So now you see the code is working. Note the output is an n by 1 vector because this is showing how much do we want to change each of the data parameters. So, we had one theta parameter for the 5 input features. This is like the first input feature, second input feature, third, fourth. It isn't that, but it corresponds with that. This is making sense? So summary again, we loop through every single data parameter from j to n. So j equals 0 to j equals n. Then we loop through I equals 0 to m. So all of the examples, loop through all the parameters, loop through all the examples here and here. And each time, this is the key expression that I use to compute that formula. Notice one tiny detail. I have like this special indexing in Numpy. I put an I comma j. So what that means is like 0 comma 4, for example. Here's a visual. So like this is the first row, 0th row, first row. And then this is the second input feature. So it could be that this is called 1, 2. That's how you index in NumPy. Making sense?